Hi students, here today the topic Faraday laws of electromagnetic induction. Short form of electromagnetic induction is EMI. There are two laws. First law, it is a statement of Faraday's first law of electromagnetic induction. It states that if magnetic flux linked with closed circuit changes, then EMF or current is induced in the circuit. It is a figure. Student, it is a figure in which cross indicates inward magnetic field into the plane and PQRS is a coil. It covers some part of the magnetic field lines. Students, when we draw PQRS coil towards left side or towards right side, then area will increase or decrease. So the number of magnetic field lines covered by PQRS coils will change. So magnetic flux will change. So in this coil, EMF or current produced, or if by any means, if by any arrangement we can decrease or increase these number of magnetic field lines. So in this way also magnetic flux change, or if we rotate PQRS coil toward this side or this side, so angle theta change. Phi B equal to BA cos theta. Okay students, if A change then flux change, if B change then flux change, and if theta is the angle between magnetic field and area vector change. So flux change. Okay students, so it states that if magnetic flux linked with a closed circuit change, then EMF or current is induced in the circuit. So here EMF or current is induced. The direction of the EMF or current is taken according to Lenz law. Lenz law. In this circuit, the current may be this side or this side. Two possibilities occur. But if we if we draw the PQRS coils towards right side, then the direction will be, and if we draw the PQRS coil towards left side, then the direction will be different. Okay, students, and after this, I am going to explain Lenz law. Lenz law. And before explaining Lenz law, I will explain a loop, current loop, in which according to the direction of the flowing current, how magnetic flux or magnetic field generated outside or in sorry below or upper side the loop. What is the magnetic field below or upper side the circular loop or rectangular loop? Okay, students. So let us see. It is a circular loop. Suppose current direction in this way, then apply current I, then apply right hand thumb rule. Right hand thumb rule. Move or rotate these fingers in the direction of the current. In the direction of the current. In the direction of the current. So thumb represents the direction of the magnetic field lines. Current is clockwise direction. So show number of magnetic field lines or the direction of the magnetic field will be inward. Inward the plane. Apply right hand thumb rule. So direction of magnetic field will be inward the plane. And second case, if current flows in the anti-clockwise in this direction, so magnetic field lines in this direction. We rotated the fingers in anti-clockwise direction. So thumb represents the direction of the magnetic field lines. Direction of magnetic field outward the plane, outward the plane. Okay, students, if current flows in this way means clockwise direction, then direction of the magnetic field inward the plane. If current flows anti-clockwise, then the direction of the magnetic field outward the plane. Please note down this. And after this, I am going to explain Lenz's law. Please note down. I have explained Faraday first law, and if we want to understand the Faraday first law more clearly, then we will have to understand Lenz's law too. Okay, sure. It states that the direction of the induced EMF or current is such that it opposes the change in magnetic flux linked with closed circuit. If due to some regions, and three regions may be magnetic field and area and theta, and if magnetic flux change due to these three elements, so EMF or EMF induced, but the direction of the induced EMF is decided according to the Lenz law, and the direction will be decided according to the Lenz law. So, what is Lenz law? It opposes the change in the magnetic flux. Direction of the induced EMF or current is such that it opposes the change in magnetic flux. If magnetic flux is increasing, then according to the Lenz law, induced EMF will be in a direction that magnetic flux should be decreased. And in other words, I can say that if magnetic flux is increasing, then current is increased. So, according to the Lenz law, the direction in this way that magnetic flux should be decreased. Let us let us say by an example. In this figure, magnetic field is inward and a coil PQRS stereo is placed in this way, and that is to be expanded. And we can see that PQRS stereo coil is contracted, and we are going to expand PQRS stereo. We are going to expand this coil. So final figure. So this is the figure when we have expanded the coil. So here we can see that the number of magnetic field lines that are covered by the area of the PQRS coils increases have increased. So what is the direction of the induced current? What is the direction of the induced current in this coil or in this circuit? So here we have seen that, as we know that magnetic flux formula equal to BA cos theta. BA cos theta. Here A is increased. So magnetic flux also increases. A is increases. A increases. So magnetic flux increases. Then if magnetic flux increases, means as we know that the number of magnetic field lines invert the plane, and if area increases, then the number of magnetic field lines covered by the area of coil increases, so magnetic flux increases. So according to the Lenz law, current direction should be in this way, that decreases, that should decrease the magnetic field. So direction of the induced current should be in this way, that it should decrease the magnetic flux. As we have seen, if current in this direction, then outward magnetic field, and if in this direction, then inward magnetic field. Here in this figure, inward magnetic field, inward, and if A increases, then flux increases. So decrease if we want to decrease this magnetic field, this magnetic flux, so the direction of the magnetic flux, so the direction of the current that should flow in this wire should be in outward direction, should be in outward direction, because inward magnetic field already exists, and the area has increased, so magnetic flux increases, and according to the Lenz law, this magnetic flux should be decreased, so direction of the current should be in this way, so the direction of the current should be in this way. Okay students, here I'm going to explain again. If we expand this coil, if we expand, so the area covered by the number of magnetic field lines increases. So according to the Lenz law, this increment in the magnetic flux should be decreased by the induced current, in this way that magnetic flux should be decreased. So it is the final direction. It is the final direction of the current in the coil. In the coil. Okay, students, it is the correct explanation of the Lenz law. It is the correct explanation of the Lenz law. If any doubt occurs in your mind, then you can comment. So you can ask any question with me about the Lenz law. Please note down. After this, I am going to explain Faraday's second law. Please note down this. What is Faraday's second law? Faraday's second law is simple. Just we have to remember one thing. The magnitude of the induced EMF is equal to the rate of change of magnetic flux linked with closed circuit. Just we have to remember only the magnitude of the induced EMF at, as we have understood in previous examples before this induced EMF. So magnitude of the induced EMF is equal to rate of change of magnetic flux. It is the EMF, it is the magnitude equal to d phi by dt. It is the rate of change of magnetic flux. It is the magnitude of EMF. So Faraday's second law states that the magnitude of induced EMF is equal to the rate of change of magnetic flux. We have to remember only this thing. But if we want to understand it in a more clear way, then we should we should understand the first law and Lenz law. Then after this, we have to remember only second law. Magnitude of EMF equal to rate of change of magnetic flux. Okay, students, please note down this. I request please like and subscribe my channel. Please. Thank you.